Welcome to Simplified Physics. This is the second lecture on vectors. In the very first lecture, we have discussed about the vectors and scalars, some terminology related to the vectors, and vector additions. In this lecture, we will discuss on subtraction of vectors, resolution of the vectors, vector addition by rectangular components, multiplication of the vectors, including scalar and vector products. And throughout the discussion, we'll try to crack some of these questions and to approach the quick approach of the very first lecture on the vectors. Please search using the phrase vectors has one simplified physics for the quick approach on the first lecture on the vectors. And don't forget to subscribe. Let's begin today's lecture. Subtraction of vector. Subtraction of a vector is simply addition of the vector with a negative of a second vector. Let us suppose we wish to subtract vector q from the vector p. Then we find the negative of the vector q. Then simply using the triangle law of addition of vector, we can find the resultant r. This resultant vector r is equals to p minus q. In this way, we can define subtraction of the vector. Let us suppose two vectors p and q incline at an angle theta. So to find v vector minus q vector, find the negative of the q vector, and simply using the triangle law of addition of vector, r vector equals to p vector minus q vector. R vector equals to p vector minus q vector. In this way, we can define subtraction of vector. And what about the magnitude of the resultant vector r? R vector equals to, once again using the triangle law of addition of vector, magnitude of r is equals to square root of p square plus 2pq cos 180 minus theta. Why 180 minus theta? The angle between p and minus q, we have to choose the angle, not the angle between p and q, that is 180 minus theta. This angle here OAB is the theta, so OAB dash is the angle between vector p and vector minus q vector. That's why it's 180 minus theta plus q squared. So magnitude of r is equals to square root of p square plus 2pq cos 180 minus theta plus q square. In this way, we can subtract two vector as well as we can find the magnitude of, as well as direction as well we can find using the triangle law of addition of vector. Let's find the resolution of vectors. Let's begin with the very basic relation from the triangle law or parallelogram law of addition of vectors. If p and q are the two vectors representing the two adjacent side of the parallelogram, then the vector from the common point vector, that is the diagonal from the point, this point gives the resultant of addition of vector. So simply for the two vectors p and q, we can write r vector equals to p plus q vector from parallelogram law of vector. What about the reverse? Reverse is also correct. That means we can divide r vector into p vector and q vector. This process is in fact called resolution of vector. The process of splitting of a single vector into two vector, as in this example, or more vectors, and the sum results the original vector r. Obviously, that process is called resolution of vector. That means simply does splitting of a particular vector into two or more vectors, and sum gives the original vector. That is simply called the resolution of the vectors. And a vector can be resolved into two or more vectors. Here R vector can be resolved into P vector and Q vector. P vector and Q vector are in fact called components of the vector R. That means the vectors into which a given vector are splitted or resolved are called components of the vector or vector components. So vector components of the R vector are P vector and Q vectors. Rectangular components of the vector. A vector can be split into two or more vector. Here in the figure, a vector P vector can be resolved into the Px vector along x-axis and Py along y-axis. So the process already mentioned, that process is called resolution of vector. Here we are finding the components, rectangular components. What in fact rectangular components? If the resolved vectors are in right angle, that means components are right angles, those vectors are called rectangular components of the vectors. That means a P vector is resolved into Px vector and Py vector perpendicular to each other. These are rectangular components of the given vector P. For a given vector P, we have x and Px and Py as rectangular components of the vector, and using triangle law, P vector equals to Px vector plus Py vector. Let's see the magnitude of the Px and Py. Using simple trigonometry, we have in a right angle triangle OPM. In a right angle triangle OPM, cos theta equals to OM by MP. Is it? Exactly not. OM by OP. OM equals to, in terms of magnitude, Px. OP in terms of magnitude P. That means Px equals to simply P cos theta. That is the x component of the vector, or component of the vector along x-axis. What about the component of the vector along y-axis or y component of the vector? Use the trigonometric function sin theta. Sin theta equals to Pm by OP. Then Pm equals to Py and OP equals to P simply gives the y component as well. Py equals to P sin theta. What about the magnitude of the P itself? Simply, when two vectors are at right angles, then the magnitude of the resultant vector P is, according to triangle of addition of vector, Px square plus 2pq cos theta. Pq cos, now cos phi equals to inner angle cos 90, pq cos 90 degree plus py square. That's mean cos 90 equals to 0. So simply we can, if two vectors are at right angle, the magnitude is square root of px square plus py square, two components of the vector. Simply px equals to p cos theta and py equals to p sin theta. In this way we can find the magnitude. What about the direction of the two vectors? Direction of the P with x-axis, that is theta, is the angle. Tan theta equals to px by py. In this way we can find magnitude and direction as well for the rectangular components of a vector. And don't forget that the x component of a vector is, for a given vector P, is P cos theta, and y component, that is Py, for a given vector P is magnitude of P times sin theta. In this way we can find components, rectangular component of the vectors. In terms of unit vectors, we can write Px as a Pxi, where I is the unit vector along x-axis. Py vector equals to Py times j vector, j cap, unit vector j cap, that is j cap is the unit vector along y-axis. Thus we can write a vector p as px times I vector plus py times j vector. Now in 3D, a vector p has three rectangular components: px along the x-axis, py along the y-axis, and pz along the z-axis. Then a vector can be p written as p vector can be written as px vector plus py vector plus pz vector. So in terms of unit vector, we can write p vector equals to px I cap, that is unit vector I, plus py j cap unit vector j plus pz k cap in three-dimensional space in 3D. Okay, using the rectangular components, we can find the resultant of addition of the two vectors. Okay, let us suppose two vectors p and q are two vectors, and r is the resultant of the addition of the vector. Simply using the triangle law, we can find resultant r equals to px plus py. How can we find using the rectangular components? In fact, using rectangular components, it is more simpler to find the resultant of the addition of the vector. Let us suppose p and q are two vectors in xy plane as indicated in the figure. Now the resultant using the triangle law, already told you, r vector equals to p vector plus q vector. We have discussed about the triangle law in the first lecture. Now result of pqr into their components. Rx and y be the x component and y component along x axis, x component and y component of the vector r, that means vector along x axis and y axis. The component Rx is simply algebraic sum of the components of the vector p and x q along x axis. That means let's see, for the vector p, the x component is px and y component is py. See once again, y component, this portion gives the py. In fact, from this position to this position is the, but we have to subtract from vector started from this point, so py. Similarly, qx is the x component of the x and qy is the y component of the, and rx and ry are the, then rx equals to, rx is simply from the diagram we can clearly see that rx equals to simply px plus py, that is x component of the resultant vector r. Once again the same figure, and y component ry equals to simply qy plus py, that gives the components of the vector. In this way we can simply add the two vectors using the rectangular components. What about the magnitude and the direction? Magnitude r equals to square root of rx square plus ry square, and if you know rx and ry, then you can find the resultant r, and direction theta equals to tan inverse rx by ry, or simply tan theta equals to rx by ry. Using this relation we can find the resultant of the, and simply theta is the angle made by r with the positive x-axis. That's obvious. In this way we can simply add two vectors using rectangular components. Let's begin the multiplication of the vectors. Multiplication of a vector by a scalar. Let us suppose a vector p and a scalar or any number k. Then a scalar multiple of a vector is k. P vector is also a vector of magnitude k into magnitude of p only, not of v vector, magnitude of p only. That means if any vector is multiplied by a number, then we get a vector. That means any physical quantity, if any physical quantity is scalar multiple of a vector, that physical quantity is also a vector, and simply magnitude is scalar times magnitude of a given vector. Now what if k is positive? If k is positive, the resultant vector kp vector and a vector p have same directions remains same for the vector p, and new resultant vector kp vector have same direction. What if negative? If k is negative, the direction of the resulting vector is reverse. That means if p vector is acting towards the east, the kp vector will be acting towards the west if k is negative. Suppose k is a physical quantity which has unit. That means the unit of resultant vector kp vector will be different from p vector. Is it clear? Let us suppose an example, yum into a vector of scalar multiple. Yum is a scalar quantity, is a acceleration vector quantity, is a product of mass and acceleration. It gives the different physical quantity if yum has unit, so has a different dimension from the new quantity, or acceleration has a different dimension as compared to the yum a vector. But yum a also remains the vector, but different vector quantity, that is we call force. Let's begin a very important topic, scalar product of two vectors. For two vectors p and q, vector p and vector q, the scalar product is represented by p vector dot q vector. P vector dot q vector, read it as p vector of dot q vector, and is defined as simply p vector dot q vector equals to pq cos theta. Scalar product is also called dot product, and the resultant of scalar product is a scalar quantity. Theta is simply the angle between the p vector and q vector as indicated in the figure. Simply p and q here are mentioned. P and q are simply the magnitude of the p vector and q vector, and never read it as p vector into p vector q vector, or p vector multiplied by q vector only. It is in fact p vector dot q vector, a scalar product p vector dot q vector, read it as, and it is also called dot product. And in fact it gives the scalar quantity after multiplication, after a resulting quantity is the scalar quantity. That's why it is also called scalar product. Let's further alternative definition. Let's see, the scalar product of two vectors can be also defined as the product of the magnitude of the given vector, particular vector, suppose p vector, and scalar component of the other vector, that means the x component of the second vector, scalar component of the vector along the same direction of first vector gives the scalar product. Similarly, we can define if in the direction of q we have to find any one vector q vector, and scalar component along the same direction of the first vector, that means q dot p cos theta also gives the scalar product of two vectors. Whatever is correct, this one or this one, and these two quantity will be same. Okay, referring to first figure, once again q vector has a scalar component q cos theta. It is indicated in the figure, q cos theta, and q cos theta that is acting along the vector p. Then p dot q vector is p vector, magnitude of the p vector, times scalar component of the vector q along the direction of the vector p, that is q cos theta. Scalar component, that means then we get p vector dot q vector as pq cos theta. Okay, with reference to the second figure also, we can define as p vector dot q vector as q vector into scalar component of the p vector along the direction of the q vector, that is simply pq cos theta. So in any way you can find the scalar product of two vector. Let's see some properties of a scalar product. A scalar product or dot product simply gives the scalar quantity. The resulting quantity after the product is scalar quantity, that means pq cos theta is simply scalar quantity. P is the magnitude, q is the magnitude of the q, and cos theta, these all three quantities are scalar, so we can say the resultant of p vector dot q vector is a scalar quantity. That means simply a scalar product always gives the scalar quantity. Let's see the second property. The scalar product of the vector with itself gives the square of its magnitude. That is, for a vector a vector dot a vector is simply a cos theta. If for a angle between the same vector or angle between the two vectors acting along the same direction in 0 degree, that means cos 0 degree means 1, so we get the a square. That means the scalar product of vector itself gives the square of magnitude of the given vector. Scalar product simply obeys the commutative law. That means a vector dot b vector equals to b vector dot a vector for a given two given vectors a and b. Let's see, for a given vectors a vector and b vector, a vector dot b vector equals to a b cos theta. By definition, similarly b vector dot a vector equals to b vector into a cos theta equals to a b cos theta. And from these two relations we can say that a vector dot b vector equals to b vector dot a vector. So we can say that scalar product of two vectors obeys commutative law. Now once again, that's scalar product of two vectors obeys the commutative law. And the dot product or scalar product obeys the distributive law as well. For three vectors a b c, a vector dot b vector plus c vector is simply a vector dot b vector plus a vector dot c vector. The scalar product of two vectors will be maximum in certain condition if they are in parallel or they are acting in same direction, and is 0 when they are perpendicular to each other. So for the parallel vectors acting in same direction or opposite direction, cos when acting in same direction, a dot b dot equals to ab cos theta, that is ab maximum value you will get. And when theta equals to 90, that means when angle between the two vectors is 90 degree or they are acting perpendicular to each other, in such condition a vector dot b vector equals to 0 degree. Not a 0 degree. A vector dot b vector will be 0. and note down the some points. For the unit orthogonal vectors, when orthogonal means perpendicular vectors, I, j and k are the unit vectors acting along x-axis, y-axis and z-axis. So I dot I equals to 1. That means I cap, both of these have the magnitude 1 1. Cos 0 degree equals to 1. So you'll get I cap vector dot I cap equals to 1. Similarly, j cap dot j cap, k cap dot k cap equals to 1. What about the I vector dot j vector? I and j are perpendicular to each other. They are orthogonal vectors. That means perpendicular vectors perpendicular to each other. That means theta equals to 90 degree. Cos 90 equals to 0 means I cap dot j cap equals to 0. Similarly, j cap, k cap and k cap I cap equals to k cap dot I cap equals to 0. They are perpendicular to each other. That's why the scalar product will be 0. And what about the vector product of two vectors? Vector product of two vectors is represented by p vector cross q vector. Read it as p vector cross q vector and is defined as p vector cross q vector equals to pq sine theta n cap. Theta is obvious. Look at the figure. Theta is the angle between p vector and q vector, and n is the unit vector perpendicular to both p and q. So minor mistakes here. In fact, p and q are the magnitudes of p vector and q vector. Simply p and q are the magnitudes of p vector and q vector, and p cross q, read it as. Okay, let's proceed. What does vector product means? The vector product of two vector gives the area of the parallelogram. I have shown in the third diagram here. Area of the parallelogram. Okay, simply magnitude of the let's begin with magnitude of the two vectors p cross q. P cross q equals to pq cos theta n cap. So magnitude is p cross q equals to pq cos theta. Pq cos theta, area of parallelogram is simply perpendicular qm by base. Qm equals to, look at the triangle OQM. Q, that is qm equals to q cos theta into base OP, that is p vector. OP equals to p vector. OP is p vector, so simply gives the area of parallelogram. That's why we can say that the vector product of two vectors gives the area of the parallelogram formed by the vectors. That thus the vector product of two vectors is the vector whose magnitude is equals to area of the parallelogram formed by them. Better formed by them, not the. So simply a vector product of two vector gives the area of the parallelogram, magnitude of the area of the parallelogram. So let us suppose two vectors p and q are acting, p vector acting OP direction, q vector acting OQ, then the area of the parallelogram formed by these vectors gives the magnitude of the vector product of the two vectors p and q vector. What about the direction? To find a direction, call the finger. Take the reference of the first figure. Call the finger of your right hand. from the first vector towards the second vector, from the first vector towards the second vectors. Then the thumb indicates, thumb is not called, thumb indicates the direction of the vector product of p vector and q vector. That means if you call the finger from p to q, thumb directs upwards, that means p cross q is the direction of the, this direction is direction of the p cross q. What about the direction of q cross p? Q cross p, now we have to call the finger from the vector q to vector p. Thumb is not closed, thumb just directed upward or downward. Now thumb directs geometrical meaning of vector product. Simply, vector product of two vector gives the area of the parallelogram formed by the vectors. That means the vector product of two vectors is simply is a vector whose magnitude is equals to the area of the parallelogram formed by the vectors. Here vector p vector is represented by vector op and q vector is represented by oq, and angle between them is theta. Then p cross q vector is simply the magnitude of p cross q is area of the parallelogram formed by OPRQ, and the area of the parallelogram is QM by QM into OP. QM into OP. OP is a p vector, so magnitude of the OP is p. What about the magnitude of the QM? QM in right angle triangle OQM sin theta equals to q times of sin theta equals to QM by vector q. Simply QM equals to q sin theta. So the magnitude of p vector cross q vector is pq sin theta. Well, let's see some properties of the vector. Vector product simply gives the vector quantity, that means p cross q vector or a cross b vector simply gives the vector quantity. The vector product of vector itself gives the null vector. That means for a given vector a vector cross a vector, that means both the vectors representing the same vector, that means angle between them is 0 degree, simply gives the null vector. Sin 0 degree equals to 0, so null vector. And vector product does not obey commutative law. In case of the scalar product, it obeys. And for a given vector a cross b, for vectors a vector and b vector, a vector cross b vector is not equals to b vector cross a vector, but a vector cross b vector equals to minus b vector cross a vector. That means they have exactly opposite direction. A vector cross b vector is a negative of a vector b vector cross a vector, we can say. Simply look at the previous diagram once again. In this case, let's say p vector cross p vector is directing upward. What if we take the q vector cross p vector? It will be vertically downward in this vector, so they have opposite direction. Commutative law is not obeyed by vector product. Now let's go for the next property. Distributive law is obeyed by cross product as well. That means a vector cross b vector plus c vector means a vector cross b vector plus a vector cross c vector. The cross product of two vectors will be maximum when angle is 90 degree. That means two vectors are inclined at 90 degree or right angle to each other, and 0 if they are parallel or anti-parallel. That means when theta equals to 90 degree, a cross b vector equals to simply ab n cap, because sine 90 degree equals to 1 when theta equals to 0 degree or 180 degree. In such condition, a cross b vector will be 0. Let's check for the unit orthogonal vectors I, j, k. I cross I acting in the same direction, that means angle between them is 0 degree. That means simply we'll get the 0 for I cross I, j cross j, and k cross k. What about I cross j vector? I cross j vector gives the k vector, j cross k vector gives the I vector, and I cross k cross I vector gives the j vector. What about the j cross I? Obviously minus k, k cross j minus I, and I cross k gives the minus j vector. Taking the order I, j, k, if they are in order, you'll get the third unit vector I cross j, k vector, and so on. Let's see some examples of the dot product and cross product. Dot product, we can say work done is a scalar quantity, but it is a scalar product of two vectors, force vector and displacement vector, that is a scalar. Similarly, power P is a scalar product of force vector and the velocity vector. Some example of the cross product or vector product: linear velocity in rotational motion, b vector equals to omega vector cross r vector, and angular momentum, L vector equals to r vector cross b vector. These are some examples of vector product and scalar product of two vectors. This is the end of the lecture. Don't forget to subscribe, and thanks for watching. Keep on watching. Thank you at all.